Good afternoon, everybody. Hope you're all healthy and safe. So, let us continue with our chapter 5 of the first module. In this lecture, we shall be discussing about a proposition, proposition 5.2.7. The proposition states that del lambda, that is, in the previous lecture, we had seen that del lambda is nothing but the image of t lambda. Del lambda equal to x implies kernel of t lambda equal to 0. Okay, that is, we are saying that if the operator t lambda is onto, then it will be 1 1. Kernel t lambda equal to 0 implies the operator is 1 1, and del lambda equal to x, that is image of t lambda equal to x, that means t lambda is an onto operator. Then the same result holds for the dual also. Okay, so we'll prove just for the operator t lambda, and the dual will be proved in a similar manner. You can try it out. So let's move on to the proof of this proposition. So we'll be proving this proposition by assuming that the result does not hold. That is, suppose that del lambda equal to x and kernel of t lambda is not equal to 0. We have to prove that it is equal to 0, but we are assuming that the result is false. So if kernel of t lambda equal to 0, there exists an element x dot belonging to this kernel such that x dot is not equal to 0. Okay, kernel of t lambda is not equal to 0 means there are some elements which are non-zero, but that is what we are considering. Okay, so x dot is not equal to 0. Now x dot element of kernel of t lambda means t lambda of x dot equal to 0, but x dot is not 0. Okay, now as we have supposed that, or as it is given to us, that del lambda, that is the image of t lambda equal to x. Okay, image of t lambda equal to x, there exists some x1 in x such that this t lambda acting on x1 will give us this element x dot, because x dot is an element of kernel of t lambda, x dot is also an element of x, right? So we can find some x1 such that t lambda of x1 is equal to x dot. So if we are proceeding in this continuously, okay, proceeding in this manner, we can say for every k, okay, t lambda of xk equal to xk minus 1. That is, for every k we can find some xk element of x which satisfies this equation, that is t lambda of xk is equal to xk minus 1. Now we have for each xk, t lambda raised to k of xk will be equal to x dot. How can you say that? Simple, we just have to apply t lambda of xk again and again, right? T lambda on the operator again and again. So here t lambda of xk is xk minus 1. So when we apply t lambda again to this operator, we get t lambda square of xk, right? So this will be actually t lambda acting on xk minus 1, right? T lambda of xk is xk minus 1. So t lambda of xk minus 1 is what? Xk minus 2, right? So if we proceed like this, when we reach the stage t lambda raised to k acting on xk, what do we get? We get it as to be x dot. That is, when t lambda is acting 2 times on xk, it becomes xk minus 2. So when it acts k times, it will become xk minus k, that is x naught. Is it clear? T lambda of xk is equal to xk minus 1. Okay, we know we can obtain it in this manner. So when we apply T lambda again and again repeatedly, we will obtain T lambda raised to k. Xk is x dot. Now this x dot is not equal to 0, right? Keep that in mind. That is what we had assumed. Now T lambda raised to k of xk is equal to x dot, and it is not equal to 0. But if I apply it one more time, that is T lambda raised to k of k plus 1 of xk. Okay, now what will this be? This will be T lambda acting on T lambda raised to k of x, right? Xk. Now what was T lambda raised to k of xk? It was x dot. That is what we had obtained just now. But x dot is an element of kernel of T lambda, so this is equal to 0. Okay, that is up to k. What have we got? So we have obtained, I'm just writing it again, T lambda raised to k of xk is not equal to 0, but T lambda raised to k plus 1 of xk is equal to 0. So if we consider, if we let, this is just a notation, nk to be the kernel of T lambda raised to k. Okay, if nk is kernel of T lambda raised to k, what is kernel of T lambda raised to k? It is a set of all x such that T lambda raised to k of x is equal to 0, right? So if nk is defined to be the kernel of T lambda of k, then we can get a relation nk is always contained in nk plus 1. That is using this result, that is T lambda raised to k plus 1 of xk is 0, but T lambda raised to k of xk is not 0. So if you take any element of nk, that is kernel of T lambda raised to k, then that will clearly be an element of raised to k plus 1, but the converse need not be true. Okay, this relation is obtained by the result that we have just now got. So nk is contained in nk plus 1. Now all these kernels they form a closed subspace. So here we will apply our lemma, the first lemma that we had seen, 5.2.1. we obtain an element, say yk plus 1 is an element of nk plus 1, okay, such that the norm of this element is equal to 1 and the distance from yk plus 1 and 1 space less than k plus 1, that is nk, will be greater than equal to 1 by 2. So this is what our lemma states. Okay, so we have obtained this much. Now we need to get a contradiction, because we have assumed that the result is false. So to obtain a contradiction, we will show that the set T of yk, okay, has no convergent subsequence, So this will imply, what will this imply? T is not compact, which will be a contradiction. Okay, so we'll be using all the things that we have obtained so far, and we will reach, or we will show that set the sequence T of yk has no convergent subsequence, so which will imply that T is not a compact operator. So let's see. Before checking whether it has a convergent subsequence or not, I'm going to consider an element z equal to yn plus T lambda of yn by lambda minus T lambda of yk by lambda, okay, where k is greater than n. Okay, now I'm going to claim that z is an element of n k minus 1. Okay, so how can we prove that? We'll see the proof of this claim. That is, we need to show that t lambda raised to k minus 1 of z, that is nk minus 1 is kernel of t lambda raised to k minus 1. So t lambda raised to k minus 1 of z should be equal to 0, right? This is what we have to prove. Now what will be t lambda raised to k minus 1 of z? It is t lambda raised to k minus 1 acting on yn plus t lambda of yn by lambda minus t lambda of yk by lambda. So let me take this inside. So this is t lambda raised to k minus 1 acting on yn plus this will together become t lambda raised to k acting on yn by lambda, and this will become again t lambda raised to k acting on yk by lambda, right? So keep this in mind. Now all these terms must be equal to 0, right? So let's see. By the definition of our t lambda raised to k yk, we have seen that t lambda raised to yk is an element of nk, right? Let me just write it out. Yk is an element of nk. So this implies t lambda raised to k of yk is 0. So one term is 0 directly. Now if n is less than k, then we know that nn will be contained in nk. So this implies if yn is element of nn, then yn is an element of nk also, right? So this implies t lambda raised to k of yn will also be 0. Okay, also if we are considering n less than k, so n equal to k minus 1 is a possibility. So if n is equal to k minus 1, this implies nn is equal to n k minus 1. Therefore yn is an element of n k minus 1, and this implies t lambda raised to k minus 1 of yn is also 0. If n is not equal to k minus 1, n is less than k, so it will be n will be less than k minus 1. These are the possibilities that is possible, right? Either n is less than k minus 1. So when we are considering the case of k minus 1, n can be either equal to it or it can be less than k minus 1. So if n is again less than k minus 1, again I can say that nn is contained in n k minus 1. Therefore t lambda raised to k minus 1 of yn is again 0, right? So I have got all the three terms are actually nothing but 0. So I will get t lambda raised to k minus 1 acting on z is nothing but 0, and this implies z is an element of nk minus 1. Okay, now we will come to the proof of the the proof of the statement that set t of yk has no convergent subsequence. Okay, so let's see how we are going to prove this. So we'll do norm of tyk minus tyn. Okay, I'm going to replace this t by t lambda. So if I replace this t by t lambda, this will be nothing but t lambda yk plus lambda yk minus t lambda yn plus lambda yn. I hope you have understood this. Why? Because t lambda is nothing but, I'm just going to write it over here, t lambda is t minus lambda I, right? So t lambda of yk will be t of yk minus lambda of yk, lambda I of yk, that is yk itself. So if I add lambda yk on both the sides, what do I get? I get t of yk itself. So this is how I have replaced t by t lambda plus lambda. Alright, so now let me just replace or just write the terms together. Lambda yk minus I have lambda yn minus t lambda yn and minus t lambda yk, right? I can write this term as, this should be plus, sorry. I'm just taking lambda yk and grouping all other terms together. So lambda yk minus lambda of yn plus t lambda yn minus t lambda yk. Okay, so we have just now seen that this is nothing but our z, and z was an element of lam n k minus 1, right? Wait, this was not our z, we have an extra lambda in it, right? So I'm going to take this lambda out common. Okay, by the property of norm, I'm taking this lambda out common, so this will be yk. If I take lambda, there will be yn and 1 by lambda, so I'm taking it inside, so I'll get yn by lambda minus again t lambda of yk by lambda. I hope you guys have understood it. Okay, now this term is what was it? It was nothing but z. Okay, so what did we state by lemma 5.2.1? We had stated that distance of yk plus 1 and nk is always greater than equal to 1 by 2. So here we have obtained that norm of t of yk minus t of yn is equal to modulus of lambda into norm of yk minus some element of zk, sorry, element of nk minus 1. So by our lemma, this will be greater than equal to modulus of lambda into 1 by 2. This implies t of yk has no subsequence. Hence this is our proof. So what we had assumed was wrong, and we have assumed that the space or the kernel of t lambda is not equal to 0, but we got a contradiction to the fact that it will be a compact operator. It will not be a compact operator. So that is what our proposition states. It states that if image of t lambda is equal to x, then kernel of t lambda will be equal to 0. So just go through the proposition once again till the concept is clear. So that's it. Thank you. Stay home, stay safe.